Welcome to a cinematic safari into the microscopic wild of our universe. Today, we're going to observe the thrilling natural phenomena of heat and exactly how it travels from one place to another. We're going to track energy right in its natural habitat, watching how it moves, interacts, and basically shapes the physical world around us. So, go ahead and get your field notebooks ready, because this is going to be a seriously fascinating journey.
To make sure you absolutely master every habitat of energy for your upcoming Grade 7 exams, here's our expedition map. 1. Heat versus temperature. 2. Conduction in solids. 3. Conductors and insulators. 4. Convection currents. 5. Radiation in space. And finally, 6. Absorbing and reflecting. Let's dive in.
Section 1. Heat versus temperature. Defining the beasts.
Heat and temperature are incredibly easy to confuse, but in science, they are entirely different beasts. Heat is the actual physical energy that makes things warm. It's the active force that flows between bodies. Temperature, on the other hand, well, that's just our human way of tracking that energy. It's really just the measurement of how much heat energy an object currently holds, which we capture using a tool like a thermometer. So, think of it like this. Heat is the invisible creature, while temperature is simply the footprint it leaves behind.
And this brings us to a fundamental law of the wild. Heat has this natural instinct to migrate. Just like water finding its level in nature, heat energy will continuously flow from a warmer body to a cooler one. It's a guarantee. If you add heat to a system, the temperature rises. Lose heat, and the temperature drops. But here's the kicker. That energy won't stop moving until an absolute perfect balance is reached across the entire system.
Section 2. Conduction in solids. Direct physical contact.
Okay, so conduction is all about direct contact. Imagine a metal pot resting on a hot stove. The stove doesn't just magically make the whole pot hot instantly, right? Actually, as the microscopic particles at the bottom of the pot touch the heat source, they gain kinetic energy. They literally start to vibrate frantically, and because they're packed so tightly together in a solid, they immediately collide with their neighboring particles, passing that kinetic energy along, particle by particle. It's a chain reaction until the heat has stampeded all the way to the top of the pot.
Section 3. Conductors versus insulators. Encouraging or blocking.
Now, metals like copper, aluminum, and stainless steel, they are excellent conductors because their particles are densely packed, which allows that vibration to just sprint through the material. That's exactly why we use them for cooking pots. But on the flip side, insulators like plastic, wood, Teflon, and styrofoam are poor conductors. They stop that stampede of heat right in its tracks. This is why appliance manufacturers use these materials for pot handles to protect our hands from burns. We even use insulators like styrofoam to build coolers, trapping the cold in and keeping the heat out.
Section 4. Convection currents. Fluid heat movement.
So unlike solids where particles are stuck in place and can really only vibrate against each other, the particles in liquids and gases have the freedom to physically roam around. Convection is the transfer of heat by the actual physical movement of the fluid itself. And when these fluid particles heat up, a truly beautiful natural phenomenon occurs in the water or the air around us.
Let's observe this magnificent cycle in action. Step 1. As the fluid, let's say water at the bottom of a pot, gets warm, its particles move faster and spread further apart. Step 2. Because they're spreading out, the warm fluid actually expands, takes up more space, and becomes lighter, causing it to majestically rise right to the top. And then step 3, once it reaches the top away from the heat source, it cools down. The particles slow down, the fluid contracts, becomes heavier, and sinks right back down the sides. This continuous looping migration of particles is called a convection current, and it just repeats until all the fluid is perfectly warm.
It is absolutely fascinating how we humans harness these exact same convection currents in our own artificial habitats. Think about your living room for a second. We strategically place heaters near the floor. Why? Well, because we know that as the air heats up, it's going to naturally expand and rise, filling the room with warmth. Conversely, we install air conditioning units high up near the ceiling. They blast out cold air, which naturally contracts, becomes heavier, and sinks down into the room. We're creating a perfect artificial climate, all through convection.
Section 5. Radiation in space. Heat transfer in space.
Now think about the sun. It's millions of kilometers away. There is a massive, incredibly vast void of empty space between the Earth and the sun. There are no solid particles to vibrate, no fluid particles to rise and sink, and yet we feel its warmth perfectly on our skin. How does that happen? Through radiation.
Radiation is the transfer of heat in sweeping, invisible waves. It requires absolutely no solid, liquid, or gas particles to travel. It operates entirely on its own, moving right through the great void.
And this brilliantly illustrates the concept. The word radiation actually comes from the Greek word radius, which literally means a ray of light. Just like light waves, heat waves can travel straight through empty space. But you don't have to go to space to experience this. If you're out in the wild on a cold, freezing night and you stand near a blazing campfire, you're going to feel the heat on your face. Even though the air particles between you and the fire are freezing cold, the radiated heat waves from the fire travel right through the empty spaces between those air particles to warm your skin directly.
Section 6. Absorbing and reflecting. Interacting with heat.
All right, so the crucial point here is how different surfaces actually react to those radiant waves. Dark, dull surfaces are like thirsty sponges. They eagerly drink in and absorb radiated heat. If you've ever worn a black t-shirt on a blazing sunny day, you have felt this instantly. However, silver or white, glossy surfaces, they act like shields or mirrors. They don't absorb the heat. They act as reflectors, bouncing that radiant energy right back out into the environment, keeping the object underneath nice and cool.
Let's look at how we apply this survival tactic in the real world. Have you ever noticed that large industrial petrol and fuel tanks are almost always painted a bright, reflective silver or white? That isn't just for looks, I promise you. By reflecting the sun's radiated heat, the surface keeps the highly flammable interior cool. It prevents the fuel from heating up, expanding, or evaporating. It literally stops dangerous pressure from building up inside the tank, completely mitigating the risk of a catastrophic fire or explosion in extreme heat. It's a total lifesaver, and it's all based on the simple science of reflecting radiation.
As we wrap up our great energy safari today, let's test those tracking skills with one final exam puzzle. Based on everything we just explored together about convection, specifically how fluid behaves when it cools, contracts, and gets heavier, why does a floating ice cube actually cool a glass of water from the bottom up? I want you to really think about the migration of those cold water particles around the ice. Thank you so much for joining me on this explainer. Keep observing the wild world around you. Best of luck with your exams, and I'll see you on our next expedition.